guys, welcome to video 2 of my Intro to 3D Art series. So today we're going to be talking about the dreaded 180 degree flip. Now what exactly is that? Well, here is a familiar sight, as crude of an example as it might be, of a forearm and hand twisting. And then doing something very strange. What exactly is this? Well, if you're familiar with 3D animation, you know this as a candy wrapping problem. Now, what exactly is a candy wrap? Well, let's go ahead and take a closer look. It is when the vertices being shared between two influence objects, being joints, are causing the vertices to converge towards the middle and then flipping and going back out to their origin. Now, why is this a problem in 3D? Well, it is more or less a problem with the limitations of vector math and quaternions. It's a fancy way of just saying a bunch of math that is limited to what we were able to do in 3D. Again, this is a limitation that you're going to have to accept. But when have you seen 3D animation where the character's arm is twisting in on itself? There has to be a workaround. Well, of course there is. A lot of people suggest to use something called, instead of classic linear, to use dual quaternion. Now, by dual quaternion, let's see if it fixes our problem. It's looking pretty good until, what the heck is going on there? That is the example of the 180 degree flip. If we look here, we're at exactly 180 degrees. If we go one step further, it flips. So quaternions will help us out to an extent, but I highly recommend to not use them unless you don't want your character rig to scale, because quaternion skinning does not allow you to do that. So that's no good. So let's look a little deeper into this and see what the heck is going on. Well, C is the influence object that we want to do and wait between A and B. So let's move B in a very strange fashion here. And let us move A and see what the heck is going on. What is going on there? It was moving smooth and suddenly it wants to snap around. So what is going on? Well, I have an arrow to illustrate, and let's see what the heck is going on. It suddenly flips direction. Whoop. Sometimes you might notice this as a pop. Other times you'll notice this as a sudden shift from left to right or up and down. Just depends what reference that the computer program decides to use. Now, what I mean by reference is, and this is very important, is that the 3D program decides to choose a reference point. Now, for us, we already have a perspective. We are using up, down, left, right as a reference. We know that the ceiling's up here. We know that this is left, or this, depending on which respect we're doing. And we know which is down, yada, yada, yada. So let's say we're twisting something. Everything looks good. We're going towards 90. Everything's hunky-dory. And then we hit 180. So we're like, and this is what we expect to happen. We expect the 3D program to hurry along and then finish and continue going all the way around to, I don't know, up to 360 and be in the positive direction. But I strangely did not put a positive number here. I put a negative number. Why negative 90? And I'll show you. So as this goes around and hits 180, your 3D program says, okay, well, which way's up? Oh, I know. This has got to be up. And I'll just pick at random. So now we're going from negative 170 or 80 and going down towards negative 90 and now going towards 0. So we don't want that. What the heck is that? How is that going to be useful for us? Any logical person would say no, go past 180 degrees, go to 270 and go up to 360. Well, the 3D program doesn't like to do that. So as you hit 180, it wants to flip and say, now this is up and this is down. And now we're going from 0 to negative 90. and then back to 180, negative 180, until it hits negative 180 again. And then decides to flip again. And then do the same thing and then go back in on itself. So this is a bit of an issue. And I bet you're pulling your hair out saying, well, there's got to be a way to do that because quaternion math gives you a reference point. Well, we never gave the computer a reference point. From the computer's perspective, this is what's going on. So which way is up and down? So, oh, that looks better. That's not up and down anymore. So that is the computer's perspective, and it's doing the best it can do. So we need to actually tell it which way's up and which way is down. Let's look at a little bit of an interesting example here and a bit of a workaround. So sometimes we use something called an aim vector. And what that is you're telling the computer which way's up, which way's down, which way's left, which way's right, which way is forward, which way's back. It's giving it a reference point. But we still need a way to compare things. So what we do is use something called a twist extractor. Sometimes people have different names for these things. So we wait between A and B. This will become C. And as we twist, this is going to have the limitation of the 180 degree until it decides to flip. So what we do is now we use something called a twist inserter or insertion by using the aim vector, the twist extractor, and then weighting that in between these two. So it has a frame of reference. We then can use the twist extractor, and since it's going to be half of what this is, because this is not moving, we can use multiplication, divide it by 2, and then insert it into the halfway point, and then distribute things respectively. That will give us 360 degrees until we notice the flip. That is the very, very much the most it can possibly do for us. It can't go past 360. 359 degrees is the most you're going to get before it's going to flip. But how often are you going to twist a limb all the way around until you break an arm or something like that? So, and you get the added benefit of having as many points as you need and many influence objects to remove the candy wrapping effect. So in effect, this is a very crude way to propagate this. There are probably way better methods, and we'll get into those later. But this is just one idea to illustrate how you get around the 180 degree flipping problem and just kind of mitigate it and turn it into a 360 degree flipping problem. So I hope this illustrates what exactly is a 180 degree flip. It's nothing you did wrong. It's just a limitation of matrices and the math under the hood. And yet again, it's an example of stuff like gimbal lock and the 180 degree flip and what candy wrapping is that might make you think that you're doing something completely wrong. In actuality, it's just a matter of understanding that this is the limitations of 3D, of the math. And what you have to understand is that many people have made workarounds to lessen the effect of this. So knowing the rules of the game, of the program, that means you'll be able to sort of bend them to your will and use them so you're not really approaching the problem with unknowingly. And that is basically the best way I can teach 3D is knowing all the limitations first and deciding how to use them in a way where you could stay far away from them as possible. And just by doing that, your work will look 100 times better than it wouldn't by just dealing with it and not knowing why. Anyway, if you have any comments, questions, I'll get into this aim extractor, aim vector, and this twist extractor stuff way later down the line. I just wanted to briefly touch on it and discuss how it could help us remove this problem. A lot of 3D is unfortunately a lot of workarounds, but you won't have to do too many of them if you keep things simple. Anyway, I hope that helped, and good luck.